us. So with these words, I would like to introduce Dr. Gypsy Nardoni. He is the director and owner of IT and Nardoni Institute of Advanced Non-Destructive Testing, Brescia, Italy. He is the president of Italian Society for NDT, as well as president of International Committee on NDT. All by the grace of Almighty, he is having 56 years of practical experience coupled with his research experience in the area of NDT. He has referred to the organization as the greatest gift from Almighty God we can make to the new generation of NDT and evaluation. INT Nardoni Institute, Brescia, founded in 1988. He has trained numerous engineers in various NDT techniques. His own son, Petro Nardoni, is level 3 certified and has been professionally trained by him as his own, as other, I would say, his candidates or participants. And I believe that this will continue the legacy of NDT in Europe and around the globe. Now he is extensively involved in industrial NDT related services. He is able to devote considerable amount of time for active research in the field of NDT. At this age, he is 81. Unbelievable. I would say there would be no one in this very world at the age of 81 who would be working in the lab. Working in the lab like a director and like a technician. No one, I can assure you.
My friend, you are doing the conference.
Okay, just 1 minute.
It's enough.
It is the blessings of Almighty on him in this regard. Actively working at this age is an inspiration for all of us. You are an inspiration for all of us. He has good number of publications in reputed journals in the field of NDT and is involved in publishing research at this age also. Presently, he is involved in Warning developing project to measure corrosion of subsea pipelines. With that from Norway. With these words, I conclude, and the whole platform is towards Giuseppe Nardoni.
I am very happy. Thank you for so long range. I start. I am very simple. I just like a work, and I am curious. And always I try to, you understood? It's okay, you all of you listen what I'm speaking?
Yes, we are listening you. We are listening you.
Thank you. So you are now, I speak with people that are India or in Oman.
Yes, we have people from India, from Oman, from Kashmir, and from New Zealand also. We have one participant from New Zealand.
I never been in Kashmir, I never been in Oman, but I was many times in India. And I had a very good relation with one of your greatest people, specialist in NDT, was Bandar Raj. Now he died, and he was director of the Indira Gandhi Institute. And in India, I have a very good, and I have a book also here, more than one of your greatest scientists. He was also president, the man, the professor, the engineer that gave up to the first mission with missiles and this. How is the name? You know?
APJ Abdul Kalam. Dr. APJ Abdul Kalam.
Okay, great man. Always he say, I read his book, fantastic. I never met him, but in any case, I know him because I read his books. And there is one part in his book, he say, I know that when I solve a problem, 50% is because I solve with my mind. But the other 50% comes from God. So this remind me very strong in my mind. So, okay. What I more shortly, yesterday, I was attending a workshop with NATO, and because we are involved in a research in inspecting the pipelines under the sea, undersea water, and I was presenting my research, and during the conference, there was an interesting paper that is on the line in which I am working, and is on the line of the quantistic physics. So the first message is the following: ultrasonic, very important, and we already reach a good part, a good level to detect defect in the well, in the wells, in the material, in the plates and everything. But we have not much knowledge how to evaluate the fatigue state of material, because there are pipelines, there are structure, pressure vessel, bridge that are working from more than 30, 40, 50, 60 years. What happens? Are those materials still fresh, young to work because they still have their properties, or they are a little old? The new physics, I am doing research in quantistic physics, but not research theoretical. Absolutely. I am really an experimental man. But you have to look a little. Problem is say to stop. It's fine, everything okay. So
Yes, sir.
in parallel to the ultrasonic and physics and so on, I embrace some years ago the quantistic physics. And from this quantistic physics, I try one of very important things. That means I was able to detect with acoustic emission. That means with vibration that are similar to ultrasonic, but less than, with frequency less than the ultrasonic, to detect when the electron change its spin and become a magnetic normal. So the new physics tell us that when you magnetize a piece, simple, we put a simple magnet, this simple magnet change the mind of the electron, and this mind of the electron is the spin. So when the spin change, then you have this. And in this workshop yesterday, and what is the important of this knowledge? The important is that when the spin moves, when the electron moves in the direction of the magnetic pole, it moves the matter, provoke vibration, and you can pick up. Again, in this moving, he generates waves, like ultrasonic, mechanical waves, you can pick up. So the conclusion, and then I go to ultrasonic, is the following. With this system, that means helped by the quantum physics, we can have now in the hand a part of science that can help us to determine the fatigue. And yesterday, workshop, very young ladies, good scientists, was already making experiment on fatigue sample with magnetic to evaluate the acoustic emission of the spin of the electron when they change during magnetic field. So you see, this is the new that come up. But you are in the university and you have the rule in studying, especially the frontier of the science. I am inside a company. I have to see the everyday work. If the structure is okay, if the weld has porosity, if there are cracks and so on. So we have to follow this. And only a small part of my work could be devoted to research. But still remaining in this area, I would say you the following. The small particles like the Higgs boson, the now everything, that means the world of the small particle, the quark, the now everything, and the macrostructure that we touch with the hand are not different universe. There are one universe because those small particles influence the macro universe. So there is a mistake between the high scientists. They look only to the small particle and they don't look how we touch when they become macro and they can touch with the hand. So our greatness, that means our that we are in non-destructive testing, we have the capability to go inside to connect the small and the macro. So this is the man of non-destructive testing. With non-destructive testing, we go into the material. We listen to the material with different acoustic emission, eddy current, all these things. And then if we know the physics, we can transfer and understood all this signal. Okay, this is, I would say, the frontier to one. So look and follow every day. If you go in Google, you found news, you found related research in the different, because in not much time you will have quantum computer, and the memory of the quantum computer is inside the spin. So it's a very new topics that should be regarded very interesting into the university. Now, Heisenberg and Niels Bohr are the two great that you have to follow if you like understood this part. And also, if you go in the quantistic, you have to forget that the electron go like orbits, because if the electron go like orbits, they collapse, because going as orbits, they create current, this current create magnetic test, and everything collapse. So when you look to the atom, there are different level of energy in the electron, but they don't are on the orbits, they are like in a cloud. So when you look to the atom and the electron, there are the main part of the matter, you have to look as are in the cloud with different level of energy and intensity. Now we close this part and become more practical. We speak about ultrasonic. Ultrasonic, very simple, are sound, mechanical waves, as our voice. You listen me because I generate mechanical waves. The means between me and you is air, so the air can transfer as matter. In the void, ultrasonic don't propagate. Only light can propagate into the voids. The first NDT method was radiography, and radiography started. X-ray was invented in 1895. Was Röntgen. Then Madame Curie used this Röntgen, and then the Bragg's brother start to measure with ultrasonic the interatomic distance that is of few angstroms. So the first application of radiography was not to detect defect in the material, but to measure the interatomic distance that for steel, alpha and austenitic steel, austenitic cubic cell are in the order of 2.5, 2.8 angstrom. So this was the way. Later on, we start to apply ultrasonic inspection material, plate, forgings, weld, composite material, and many other things. That means ultrasonic are not only for steel, but you can use also in concrete. In concrete, there is a correlation between the speed of ultrasonic and the strength of concrete. This is very important. This also is one of the common. Okay, there are some questions about this first part. Then we go to the second and to the third part. So you have problem, or you like to make some question about this first part, about quantistic physics, electron spin, fatigue? No question?
Sir, our head of the department, Dr. Sheikh Nazir Ahmed, who is wearing this aerodynamic cap, he is from aerospace. He is BTech, MTech and PhD from IIT Kanpur in aerospace, MTech from IIT Madras aerospace, BTech from NIT Srinagar in mechanical. Maybe he asked you because his PhD work is related to thermoelastic smart structures like that. Sir, you can interact.
So you are inside really, because you see, I believe I am a strong supporter of the string theory. String theory is the theory that is in every updated book is present. But the string theory, there are two brackets in the string theory. One is the bracket that follow the mathematical, and I don't look to this one because it's incredible. 4, 7, 8 dimension. I am only maximum 3. I am in trouble with 3 dimension. So I don't go there. But in any case, every scientist also speak about string theory. The string theory, my string theory, is that all the matter is made of very microscopic strings, very small. Because if it was not so, how can matter vibrate? And matter is like a violin. If you stress a rope, you have an harmony. You leave a little bit of rope, you have another harmony. So when you look to the metallic structure, you have to see in this view, like a violin. That means it never changes. If you make an example, why a steel become strong? I asked to 100, 400 engineers, no answer. Oh yes, because I quench. Oh yes, because I deformation. Oh yes, because I put inside carbon more. Oh yes, because I molybdenum, and so on. The real answer of the intimate phenomena is very simple. Each process that introduces stress make steel harder. Very simple. If you have in mind a very small string that are part of the universe of the metallic stuff, then it's very simple. So, and I will send you also. Okay, now go to ultrasonic. Ultrasonic are, tell you their radiography, we use ultrasonic. Why? Because with radiography you can see very well some type of defect, but you cannot see some other type of defect. Perhaps with radiography you cannot see lamination in the plates. With radiography you cannot see oriented cracks. So this way the ultrasonic comes and goes. Ultrasonic are very simple, are mechanical waves you introduce in the material, they found a reflection, and then they come back. Now we go to picture. Today, this morning, I speak you about two advanced, one of the advanced, the most accurate, the most precise ultrasonic technique that today we have to inspect the weld. When somebody speak you, do the best technique of ultrasonic, time of flight. Because with time of flight is important, and now we will go inside. The reflection don't come from the surface. That means the reflection of ultrasonic is not connected with the orientation. If you have perpendicular orientation with ultrasonic, very good signal. If the orientation change, very bad signal. With time of flight, you don't have face this limitation, because time of flight works on the extremity of your defect. That means on the extremity of your crack, on the tip. That means the upper extremity of the crack in the weld is upper tip. And now I show you with the first image. And you can interrupt me in every moment. And no, this is the okay. Go on. Okay, now. So this is the first. This is a phased array image. That means go the next one. Okay, so in physics you have a very, this is typical in every book of physics. That means if the plane waves comes from small holes that are in the order of the wavelength, you have diffraction. That means you start to have some spherical wave. Spherical wave, this diffraction is the principle of the next one is the principle of time of flight. So how works time of flight? You see, here you have one probe here and one probe here. Every day we inspect in this way hundreds and hundreds of all the world is working with this technique. All the world, America, States, Germany is the best. So one probe transfer the ultrasonic, and the second one receive. You see, when this transfer, the upper tip of the probe and the lower tip of the crack generate, look in the left, you see, in the left here, in the left you see that there is one spherical waves, and down you see another spherical waves. And this is the main wave that come over the defect. The results and the valuation of the signal are in the right. You see the upper tip and the lower tip. The distance between the two tips are the height of your crack. And this is the joy for the people of fracture mechanics people, because
Again, we are
when
not sharing screen.
what they say?
Excuse me, sir.
Yes.
If you kindly share this screen so that we see the figure what you are explaining. Yes, now it is.
Professor, it is coming. It is coming.
Now it is coming. It was not coming earlier.
Maybe some problem in your system, but our system it was coming.
Okay, okay. Thanks. How it is coming?
Please go
ahead.
My friend, you can interrupt me any moment, because
now I got it.
Sir, it's okay because outside of Kashmir, we are able to see the screen.
Okay.
But they cannot see the screen.
Now screen has come. Thanks.
Yes, because without screen, no cinema, finito, no film, no Marilyn Monroe present. Okay. So, look, this is the basic, because at the left you see what happens inside the material when the main wave, this is the, at the right side you see the main wave. This is the main wave. When they come over the crack, they generate the two spherical waves. The software make his work and project in the monitor two signals of the upper tip and the lower tip. This distance gives you, with an accuracy of less than 1 milli, the height of your crack. Also, if the crack is 3 millimeter high. So this very high sensitivity of time of flight. Next one, perhaps we can understand a little better. Here you see very nice pattern what I'm talking you. That means the longitudinal, the front of the longitudinal wave cross the tip, the upper tip, and you see it start the simulation on the upper creek. When the front of the wave hit the second tip of the crack, the second lateral it start and you go on the screen. Okay. In the right side, you see an example when how you see the tip of a crack with a standard pulsate ultrasonic. You see two echo, one the upper tip and one is the second tip. This, if you have high resolution probe, high resolution angle. Not always you can see a 3 millimeter, because this is a 3 millimeter cracks with such resolution. In the left side, you see how you see with another technique of ultrasonic is phase array. Also here you see the upper tip and the lower tip. And this is in phase array. Phase array, different of time of flight, still has limitation due to the orientation, because at least phase array is at least again a pulse echo with the different beams. Okay, now we go. Clear forever? So in your university, if you like to make experience with ultrasonic, then you have to make two fundamental type of discontinuity. The side-treated holes that are fundamental in our work for the calibration. All the code asks for cylindrical hole, and then you have to make also the slit. You see in the upper, you see the slit. These are made with electro erosion. And here, don't leave. These are made with electro erosion, and in generally we start from 3 millimeters for up to related to the thickness that you have to. But in generally, all Europe is calibrating ultrasonic on 3 millimeter diameter side drillet holes. American, through the ASME code, related the diameter of the hole to the thickness of the material. So they go also to 8 millimeter. Now, go to the next. Here you see, again, a simulation. This comes from the, I picked up this simulation in the United States when I was for a conference. And this is the spherical waves. And this is a schematic diagram in which you see that the attenuation with the spherical waves is square inverse the distance. Because you have two types of waves when you make an inspection in ultrasonic. From cracks, you have spherical. From slack inclusion and all the hole, you have planar, you have cylindrical waves. And the cylindrical waves don't go with the square of the distance, but only linearly with the distance. So you need different calibration. The next. Okay, yes. Now you can see some type of difference. You see, at the left, the first is typical lack of fusion, is a planar indication. Generally, you cannot accept in the well planar indication. Upper, you see a hole, that means porosity, slack inclusion. Slack inclusion, porosity are volumetric indication, then are more acceptable in the code. Again, in the right upper, you can see lack of fusion. Again, planar, you see different orientation. So for time of flight, very easy. If you use standard technique ultrasonic, then it's a little bit problem. So a big defect like this, when you go to see with ultrasonic, if it is oriented, you less empty. On the right again, you see lack of fusion between multipass weld. Next slide. Okay, here in weld, you have three different types from the point of view of ultrasonic. You have three types of welds. You have first degree and third degree cracks are very big cracks. You can see very easily, like the 9 millimeter. But then you have very small cracks. At the right, you see hydrogen cracks or hot cracks. They are not bigger than 3 millimeter. So for this one, it's quite difficult to detect, and you must use a very accurate technique in order to detect this small crack. Next one. Okay, so here you have the two type schematic. Left, cylindrical waves, right, spherical waves, different attenuation with the distance. Next. Okay, you see the left, you see a simulation of cylindrical wave, completely different from so it's a front line, they go back, there is no, I would say, spherical waves. This is typical for volumetric defect like slack inclusion, porosity, and this, and the right one is typical for cracks, lack of fusion, and lack of penetration. Next one. Okay, now we go in the shop. Now we know the technique, and then we go in the shop. This is a shop in which we make big vessel. We inspect this big vessel with time of flight. And here in the right, you have an example of, this is a section we call B-scan. That means this is a section of the weld. This is the thickness, and inside where you see all this indication, this was a typical weld with many defects, but it's not normal a weld like this. Next one. Okay, these are, when you make this type of examination, you need scanner. And the scanner in the left side, this picture was made in India, in Larsen and Toubro company, and it was it was in the area, in the Punjab area, in Kursania. This is Kursania area. Okay. In any case, this was in India. In our company, we make the scanner. And in this moment, 2 of these scanners are working in Spain because we are specialized in this inspection. Next one. Okay, now I present you my friends that when I learned time of flight, I met this. First one is Professor Shah. He is from Harvard Center, very great man. He make a lot of research. I had the honor to meet him, invite in Italy, and you see here is in Italy in the 80s when I ground the Italian Society for Non-Destructive Testing. On the right side here, you see Professor, this one, no, go up, a little bit up. You see, no, up, go up now. No, go down again. Okay, this is Professor Silk in the right from Harvard. He invented time of flight. So I don't go inside how we do this, but because we have other things to see. In the picture, you see my son. The first in the left is my son when we make a meeting in Italy on time of flight. Now, the next. Okay, again, you see diffraction. And again, go down. Okay, these are the different echo that come. You see this is the lateral wave, this is the back wall, these are the 2 tip, and then, okay. Then we go, okay, this is how looks a typical configuration of time of flight inspection. It means transmitter and receiver, and then you have everything. Next one. Now we go to the picture. Okay, now this is a typical picture of time of flight. We call this scan. You see, this is the thickness of the material, and this small black and white, you always see black and white. Black and white are small inclusion inside the material. We have a big reference. The brightness of the black and the brightness of the white are related to the amplitude of the signal. So if the signal are small, then you see only like you see around. It's not flat, the surface of this main. You see very small. So that means are very small noise level and so on. But when the signal achieve the calibration amplitude, then the signal appears with a brightness that I call zebra. Zebra is number one, class one. We classify. There is no a classification, but we classify in this way in order to have a better effect. Next. Okay, here you see. Now you are professor because I ask you, where is the defect? And you say, oh, my friend, I see very well. The defect is in the center. That means here you have a smaller thickness and you have lack of fusion. You see very long indication. So you, with time of flight, you can see as in radiography, but much better because time of flight show you all the indication. With radiography, you cannot see all indication. Next picture. This is a reference book. Okay, here you see that.
Sir, I want to intercept over here. Generally, we say that in radiographic examination, we are able to get the better picture of our defect. But in your presentation now, you are saying that with TOFD, these images we get the better information about the defect. So kindly explain us once again.
Yes, because in the, you see, the sensitivity of radiography is in generally 2% of the thickness. This is the request of the code. If you have 100 millimeter thickness, that means that you lose a change in thickness of 2 millimeter because 2% of 100 millimeter is 2 millimeter. What means that if you have an oriented crack or an oriented lack of fusion, what means that when the radiography pass through, they don't go through the crack. They cross the crack. And the cross distance of a crack is very small, perhaps 0.3, 0.5 milli, so you cannot see. You see, you have not enough change in the attenuation when the radiography cross the indication. So if the crack is parallel to the direction of the radiography beam, okay, you see very well, better than in ultrasonic. But in generally, the crack are not standing in a vertical position. No, they have many orientation. In particular, you know that most of the crack are in the heat affected zone. And heat affected zone, generally, you are parallel. So, please.
Yes, sir. In heat affected zone, I can accept that they are parallel, but the lack of fusion, it is on the sides. So the orientation of the defect can be, I think, properly detected with when it is towards the sides, the lack of fusion.
Because in general, the bevels are oriented, no, have an angle. So
okay.
lack of fusion in the side, and this, I think, this is one of the reasons that for heavy thickness, just from many years, you can substitute ultrasonic with, you can substitute radiography with ultrasonic.
Good.
As my code allow you to use ultrasonic instead of radiography, but if you use computerized system as time of flight or phase array, not manual.
Okay, sir.
Not
thank you. Thank you, sir. Thank you, sir.
So this is the so other question till now, please. Other question? And not also stupid question can clarify a big problem. Remember, I not necessary. Generally, we think to an intelligent question.
There is a proverb, sir. It is better to be fool for a minute than forever. It is better to be fool for a minute than forever.
So many times when I participate, perhaps to also gesture and so on. Now I am more experienced, so it's easier to make some interruption. But many times you are thinking, oh, this is too simple question. I remember I was in Korea many years ago, and one was speaking about this is smart material. So 400 people are listening. Nobody make question. I asked, please, what is smart material? He make 20 minutes discussion just to clarify smart material. Yes. This is the life. Okay. In any case, time of flight is really the most, the only limit of time of flight is the following, that you need to place the probe from both sides and not, you see here, no, stop. You see how you can see, fantastic. This is a lack of fusion again. So we have a reference collection as for radiography. Time of flight is better than radiography because you have images forever. Here you have you see, this is the thickness. You have the lateral wave up and down, you have the back wall. The other part is don't look to the other one. Again, you see lack of fusion with some inclusions. Linear is always lack of fusion. And also you can measure very high. But this smaller thickness, you see very small inclusion. When you see this arc, that means that defect is very short. So you see arc, small inclusion. Again, here some. Hey, here you see, these are again lack of fusion. You see here.
Dr. Nardoni, just hold for a few seconds. Someone's microphone is on. I request whosoever microphone is on, please kindly put it off, switch it off.
Sir, it's a HOD sir's microphone on. Sir is not there.
Ali sir, शेख सर उनको म्यूट कीजिए. शेख सर उनको म्यूट कीजिए ना, आप एडमिन हो वहां पे.
Sir, I am not the admin. Dr. Pali is the admin. Okay, that person has gone outside. I will call him. Wait a minute. Just a minute. Okay. Professor Nazir, please keep your mic off, sir, because your voice is coming in the lecture.
Okay.
You like to make questions? Okay.
Yes, sir. You can continue, sir.
Okay. So now you can also evaluate this image. I am waiting about your evaluation. They evaluate what is how you evaluate these images, good or bad.
These images are good, but there are inclusions. What these images are reflecting, it is showing
Yes.
that there are inclusions over there.
Yes, you are right. That means this is a circumferential well, and you have inclusion because you see, when you see all this arc, that means there is a distance between the different inclusions. So aligned is a typical aligned inclusion, very clear. And so it's fantastic to see. And also very important, you see, as in the sea, the image shall not be flat. You have to see some small waves, not in zebra color, but in a shadow. But you have to see, that means that this is in practice the noisy of the ultrasound that go across the material. This is the typical area of where we go. The next one, finito. Okay, so my friend, you have seen one of the most advanced technique that give the highest reliability of inspection with ultrasonic. To make this, you need computerized system. In generally, equipment like this, equipment like this, the cost is about 50,000 euro, the cost of this equipment. And also the just a moment, I have interruption here, dimmi. Ah, grazie. Hai visto che belle robe che abbiamo fatto? Eh?
Screen is not coming.
Because he's talking to some person, the screen will come afterwards. He has finished one presentation of TUFD, time of flight diffraction. So he will start with phased arrays in his next presentation.
Okay.
It will come. It will come. Inna Allaha ma sabrin.
Tomorrow. No question. Have you question?
Sir, I have a question that once again repeat the cost of the machine. You told
yes,
50,000 euros.
The machine is about 40,000 euro. About
40,000 euros. 40,000 euros, huge amount.
Yes, yes, yes. We have 10 of this machine here. Because every day we work with this machine. Because the ASME code allow to inspect with time of flight. You can avoid radiography, because to make radiography on 200 thickness, you need linear accelerator. Linear accelerator today, you need 200,000 and make the bunker about 500,000 euro to set up a facility. And then also sometimes the pressure vessel are 30, 40 meter long. There is no bunker that can take these pieces. And more, some assembly is made on site in the desert. We were perhaps 9 months in Saudi Arabia in the desert to make inspection, because all the vessel has been built inside. So this time of flight, and we have been the first using time of flight, and is able to substitute for code case, for ASME code, the inspection of ultrasonic, longitudinal waves and circumferential waves. And very interesting is also how you evaluate the indication, because the ASME code has a fracture mechanics criteria. That means when you found an indication, you have to estimate the height. And when you have the height, you have to make a ratio between the height and the thickness. If this ratio is out of the data in the table, you have to repair. Because they have calculated that the height, the true thickness height and the length can have a limit, and if they are greater than a certain limit established from the engineering of the ASME code, you have to repair. So ultrasonic, this way ultrasonic is better than radiography, because in radiography you cannot estimate the height of your indication. You have indication, you can only say the length of the indication, cannot estimate the height. With ultrasonic, you can estimate the height in an accuracy that maximum is the order of 1 milli. So it's very good accuracy. And also, in this case, the people of fracture mechanics can make evaluation. So this is the very new, I would say, but this was a code case that ASME code made, I think, 10 years ago. So just from 10 years, we are using this ultrasonic system. It's called computerized ultrasonic system. And the ASME code is really very clear in its code, in specifying the acceptance criteria, the condition to make the work, and the calibration. You need to do the validation of the test, because what we do, we have to make a procedure to make this examination. And this procedure is based on some test block. And this test block has to be validated in the presence of the inspector. So when we make the procedure, we go in the workshop, the client and the inspector say, this is the test bit with artificial indication. You must demonstrate that with your technique, you can detect this type of indication. And we have to, this is everyday work. We also today, we have 4 CAP different places. One is also in Spain that are, and one is in Egypt, that are working with this technique that I have described before. So it is good that the university is able to transfer to the new young engineer that comes out the information on this technique, the reference in which they can go perhaps to take the knowledge for this. And I ground the academia 10 years ago, and the rule of academia, I am the president actually of academia, is to promote this inspection into the university, because still now also in Italy, in the States, there are some universities that do some experience, but there is no, I would say, a specific curriculum, specific program for 6 months, 5 months, as you like, in which we explain this these techniques that are necessary for an engineer that has to make project. If you do project, you have to need which type of inspection you will do on this project. So this is quite normal. Okay, my friends, I'm available for question. Tomorrow we speak about another technique that is not so accurate as this one, as time of flight, because again, the principle is pulseco. It means the reflection is connected with the orientation. In time of flight, defect could be vertical or horizontal. No change. You can see. So you can see inclusion and you can see crack. If it is oriented, you can see. Okay.
So, sir, I request you in your tomorrow's presentation, if you could share your experience related to basic ultrasonics also, because few of our participants are new to this very technique. So if you could spend some 10, 15 minutes, 20 minutes related to basic
Okay.
ultrasonics, right,
Yes.
sir?
Okay.
And I just, as a information I want to take, in 2017, I believe in month of February, you were at Mangalore refinery for NDT.
Yes, I know.
So would you like to share your experience while working in India in Mangalore in the refinery? What sort of assignments you did over there related to NDT?
Yes. Okay, there we make inspection, and you see after 20 years, pressure vessel have big cracks. So inside the vessel, we found big cracks, and it's normal because this big vessel, they work for 20 years at 500 temperature. So, you know, by metallurgy that you have, I would say, how you say, like you have creep. What is creep? Creep is that the different layer inside the material, they are shifting. They shift, and they create at the end cracks. So we can have big cracks, and we found big cracks inside. Some also now. Also, you see directly with dye penetrant or something like that. Okay, tomorrow we will speak about the principle of ultrasonic, but because principle ultrasonic is like a radar, you send an impulse and the impulse come back. But the problem is that, as I tell you before, that defects are not real. They say, "Oh, come, I am ready to be hit by you." No, the defects are oriented. So you must choose the angle in order to be always much more perpendicular to the surface for a best reflection. This way in ultrasonic you have 45 angle beam, 75 angle beam, 70 angle beam. So you have different angle beam. I would say I prefer to give you a general vision
Generally.
in order that you know where we are, instead to make small lessons about the Sony. Instead, so you must run now because progress is going very fast. So uh, the integrity of material is number one. Especially all the material, concrete is becoming old, steel is becoming old, pipelines are becoming old. So we have to accelerate our technology in order to be able to reply. Instead, we are, as now, in the condition that we have a dramatic situation with virus, but our scientists inside the hospital and so on, the doctor and so on, really are coming late in order to understand.
Sure, boss. अच्छा يا باري الكرة كده تسري
What is the problem? Problem? Question?
Adam, yes, yes. Any question, sir? Okay, just at last, I would like
Yes,
to
sir, one
ask you,
question.
would you like to share your experience just like that? Na? A doctor is very happy when he saves the life of his patient. He's getting very happy. So maybe in NDT, what is your so many years of experience that I did this NDT, and if I would not have done it, this structure would have burst, or there would have been a major accident if I would not have done this very NDT at this time. Do you have some sort of experience like this, that I saved so many people's life while doing my job in a professional way?
What is that? What is that? No.
I am telling you, sir,
Yes.
just like a doctor feels a lot of happy, he feels very happy when he saves the life of the patient. Similarly, in your this 40-50 years of experience, when you did lot of non-destructive testing of many structures, oil refineries, pipelines, so what
Yes.
if you would not have conducted this very NDT in this time, the structure might have burst and many people would have died. So you feel some sort of pleasure that I did my job professionally at the right time, and I gave my
Yes,
best.
I can reply very, very easily. That means when I start to work, I was in a very big company, 2,000 people, and we make pressure vessels. And I started with radiography. I was young, 18 years, just out from technical. And after 9 months, I stayed there just to see how we steal and so on and so on. And then the president called me and said, Nardoni, you are responsible for the integrity of the material. Go around the world, do everything, but I like to produce pressure vessel, penstock, and everything that are sure for life, for everything. So I go around the world. That means, but not only just calling, but in the 70, just in the 70, I was in Toronto at the first meeting of International Welding Institute, presenting some of my research. That means when I start to do ultrasonic, when I start to introduce ultrasonic, because before they do only radiography, I found the situation that I detect many defects, meter long of defect in the weld, and radiography was okay. So I create a problem in the company. So at that time, the director of the production say, Nardoni, radiography are okay, I send the material. I said, you have to do this. No, I don't do the certification because I have found cracks. So for me, the piece has to stop. Okay, so it was a query between me. I was not a manager at the time, and he was a director. But over the director, there was the president. So I say, okay, engineer, the president in this moment is in South America. When the president come back, we make a meeting and we discuss how we have to solve this question. The president come. Meantime, the piece was still waiting. And I explained to the president that big crack, meter long, have been missed by radiography. The code asks only radiography. For the code, we can send the material. But from my point of view, about the rule that you ask that I have to do, that means to detect dangerous defect, I say, no, this material cannot go out from the company. And the president take the decision It was a great decision. He say all wells over or products with wells over 60 millimeter mandatory ultrasonic. Only after 15 years, the code requests ultrasonic. So the message I give to you is the following. The code is at least 5 years back. Technicians must live in the frontier, have to touch and take the new technology. And after, when this technology is well known, then the code make this technology standard. If you say, I do as the code, you are not in the condition to produce a safety product. This is the reality. Yes.
Thank you. Thank you.
And I add another thing, that this is also in the tribunal. Many cases in tribunal, not only for, but when they ask, are you made all the testing for this piece that create a collapse, people die? The reply of some people say, oh yes, I have made all as the code. The tribunal say, at that time when you deliver your piece, there were technology able to detect what caused the disaster today. If the reply is yes, you are guilty. This is really because we had the conference about this problem, because this is a real problem in the industry. So this way we have always to be updated, and you in the university, you must be very clear on this subject. Okay.
Okay, thank you. Thank you, Dr. Giuseppe Nardoni, for your fantastic lecture and enlightening sharing your 50 years of experience with us. I hope so. The inspiration for all of us is that at this age, you are working like I would say, young and dynamic engineer. Young and dynamic. And we pray to Almighty, live long, Giuseppe Nardoni, for the service of society.
I hope that one time to come in your university and but also an invitation to some engineer of your university to come. I'm very welcome. So very open in this case.
Yes. We will sign a MOU between your institute and NIT and Kashmir University, where you will enjoy the summers. I would say paradise in the world, the valley of Kashmir. In Arabic, we say Jannatul Ard, means heaven is heaven on the earth. If there is, it is in Kashmir. It is in Kashmir.
Okay. All the best. Bye-bye. Go to lunch. Arrivederci. Thank you very much.
Thank you, sir.
A question for tomorrow.
Okay.
Also stupid question.
Okay, sir.
Stupid, not intelligent question. Bye-bye.
Thank you. Sir.
Okay, sir. Thanks a lot.
Thank you.
Okay, good. And now we have to prepare.
Thank you, sir.